Okay, I'll be talking about integer programming-based prediction of RNA secondary structure with pseudoknots. Here is the outline of my talk. First, I'm going to talk about background of this work, reviewing previous studies for predicting RNA secondary structures with pseudoknots. Then, I'll describe our method using integer programming. After that, I'll share with you some of the highlighted results on various datasets to confirm our method. And finally, I'll make a summary and talk about future plans. First of all, let me refresh your memory on the background knowledge of RNAs. Ribonucleic acids or RNAs play an important role in biological processes, such as not only the passive role as a messenger that carries genetic information translated into proteins, but also the active roles as a regulator for gene expression and as a catalyst in the cellular processes. It is widely believed that there is a strong correlation between the structure of an RNA molecule and its function. Pseudoknot is an important topology in RNA secondary structures. This is an example of pseudoknot structure called simple type H-type pseudoknot. If we connect base pairs with arcs and stretch the sequence from 5' end to 3' end, we can get the sequence with arcs like this figure. Then we say that the secondary structure includes pseudoknots if at least two arcs are crossing each other. It is known that pseudoknots play an important role in RNA functions, such as regulation of translation and splicing. Furthermore, pseudoknots assist the foldings in the 3D space. A lot of algorithms for predicting RNA secondary structures have been developed. However, most of them don't allow any pseudoknots due to computational cost. Now, we consider the extended problem, and that is, for an input sequence, we predict the optimal secondary structure, which may include pseudoknot. Here is a summary of existing methods for pseudoknot prediction, which can be roughly classified into two approaches. The one approach includes dynamic program-based exact algorithms, which can predict restricted classes of pseudoknots. Because predicting arbitrary classes of pseudoknots have been proven to be NP hard. For a sequence of length n, the time complexity of DP-based methods are proportional to n to the 4th power to the n to the 6th power, depending on predictable classes of pseudoknots. On the other hand, heuristic-based approach can predict wider classes of pseudoknots by using pseudoknot-free algorithms iteratively or greedily. Our approach can be classified into this approach. Okay, next I'll describe our method. What you see here is the overview of our method called IPknot, which is short for integer program-based prediction of RNA pseudoknots. First, for an input sequence, approximate posterior probability distribution over RNA secondary structures with pseudoknots is calculated from by a pseudoknot-free algorithm. Then we find the optimal secondary structure with pseudoknots, which in terms of MEA principle by using integer programming. We have already applied this framework into RNA interaction prediction called LACTIP and have performed good results. Given a probability distribution over a space of secondary structures, we predict the optimal secondary structures that maximize the expectation of gain function, which represents accuracy of RNA secondary structures. The gain function is defined as the sum of the weighted number of true positive base pairs and the number of true negative base pairs. This means that we predict as many correct base pairs as possible in expectation. The weight parameter gamma controls the balance of specificity and sensitivity of predicted base pairs. For the probability distribution without pseudoknots, we have already implemented this methodology as centroid fold, which is one of the best prediction tools of RNA secondary structure without pseudoknots. For the probability distribution with pseudoknots, this calculation is unfortunately intractable because calculating the probability distribution with arbitrary classes of pseudoknots is NP hard. Even for those with restricted classes of pseudoknots, which can be calculated by DP algorithms, it requires impractical time proportional to n to the 6th power. Because of that, we approximate probability distribution over pseudoknoted structures by its factorization, in which each factor is a probability distribution over pseudoknot-free structures. Each of pseudoknot-free substructures is called a level. We can calculate them very quickly, proportional to n cubed. By using the factorization, the objective function can be approximated by the sum of the expected gain function for each level of pseudoknot-free substructures. Then the objective function can be transformed into this formula, which includes base pairing probabilities Pij. Base pairing probability Pij is a probability that the ith and j spaces form a base pair. This is an example of the base pairing probability matrix for the sequence at the diagonal. Each cell represents base pairing probability by gradation. This matrix can be calculated by the McCaskill algorithm, whose time complexity is n cubed. Our implementation employed RNA fold in VNRNA packages with the Boltzmann likelihood parameters to calculate this matrix. Then, this formula means that in order to maximize the objective function, we consider only base pairs whose base pairing probabilities are larger than threshold, because This term, which includes base pairing probability, should be positive for predicted base pairs on each decomposition level. This technique is called threshold cut. The threshold cut technique allows us to reduce the search space, like this figure. To satisfy the consistency of RNA secondary structure for the solution, the following constraints must be held for all decomposition levels. The first, each base can be paired with at most one base. Second, no pseudoknot on each level is allowed because we assume that secondary structure is decomposed into pseudoknot-free substructures. And last constraint ensures the uniqueness of decomposition of predicted secondary structure. We can probably develop sparse dynamic programming recursion to find the optimal secondary structure that satisfies these constraints. However, it is very hard to implement for such complicated constraints. And therefore, we consider the use of the integer programming. The integer programming is a mathematical optimization whose variables are restricted to be integers. In our case, unknown variables are restricted to be binary valued variables that represent predicted base pairs on each decomposition level. Finally, we can formulate the optimization problem for predicting RNA secondary structure with pseudoknots as the integer programming shown here. Each constraint corresponds to each figure at this slide. There exist several available IP solvers. Our implementation supports 2 commercial IP solvers and 1 free solver. In general, IP-based methods are very, very slow for huge problem. However, in our implementation, the threshold cut technique makes our implementation fast enough even if we use free IP solver, because the threshold cut technique allows us to reduce the search space. Let me summarize our method. For our input sequence, we approximate posterior probability distribution over pseudoknoted structure by its factorization. Each factor is a probability distribution over pseudoknot-free structures. Then, we find the optimal secondary structure that maximizes the expected accuracy of RNA secondary structures by using integer programming. The threshold cut technique derived from MA principle allows us to reduce the search space. As a result, we can find the optimal secondary structure very quickly. In order to extend IPknot to common secondary structure prediction with pseudoknots for aligned sequences, we employed averaged base pairing probability matrices, which have been developed in our previous work. We can make a prediction for aligned sequences by using average base pairing probabilities as input into the IP problem I talked before. Okay, let me move on. Computational results on various datasets. To confirm the effectiveness of our method, we conducted several experiments comparing IPknot with these competitive methods for predicting RNA secondary structures with pseudoknots and those without pseudoknots. We employed PK388 dataset for single sequences, which contains 388 sequences taken from RNA standard database. The reference secondary structure of each sequence contains at least one pseudoknot. We evaluated the prediction accuracy through positive predictive value, sensitivity, and Matthews correlation coefficient. MCC is used as a balance measurement between these two measurements. This figure shows the PPV sensitivity plots for respective algorithms on PK388 dataset. A point which is near to the top right corner means better accuracy. These triangles in red are the accuracy of IPknot, changing the weight parameter gamma, which controls the balance between PPV and sensitivity. And the dense point indicated by an arrow is the highest MCC among all the parameters. And these blue points are the accuracy of the existing method for pseudoknoted structures, and these black points are those for pseudoknot-free structures. This graph shows that IPknot around here is more accurate than the existing method. And for aligned sequences, we also compared IPknot extended by the average baseline probabilities with these competitive methods for predicting common secondary structures with pseudoknots and those without pseudoknots. We employed alpha-PK dataset for aligned sequences, which contains 67 alignments taken from alpha database. The reference alignments were realigned by cluster W to produce low quality alignment, which doesn't consider secondary structures. The reference common secondary structure of each alignment, each reference alignment contains at least one pseudoknot. Here is the prediction accuracy for the hand-calculated reference alignments. These red points are the accuracy of IPknot, changing the weight parameter gamma, and these blue points are the accuracy of the existing method for pseudoknoted structures, and the black points are those for pseudoknot-free structures. This figure suggests that one of the existing methods, HX match, and IPknot are comparable. Here is the prediction accuracy for cluster W alignments, which don't consider any secondary structure. This graph shows that IPknot is more accurate than the existing method on cluster W alignments. And comparison between the comparison of the results between the reference alignment and cluster W alignment suggests that IPknot has the robustness against the alignment error compared with the existing method. In general, making high-quality structural alignment is very expensive, and therefore the robustness against the alignment error is of great benefit. We evaluated the time performance of IPknot. These 5 sequences of various lengths were used to measure the elapsed time. This table shows that IPknot is much faster than the existing method for pseudoknoted structures and comparable with those for short-free structures. Let me summarize my talk. We develop IPknot based on maximizing expected accuracy using integer programming with threshold cut technique. Our experiment shows that IPknot enables us fast and accurate prediction of pseudoknotted RNA secondary structures. Our computational framework, which consists of approximate probability distribution, maximizing expected accuracy, and integer programming, is very powerful. We have already implemented, applied this framework into RNA interaction prediction called RACTIP, and this work IPknot. We are planning to develop several applications of this framework, including these applications. The source code and executable binaries of IPknot is available here, and web server is also available here. I'd like to thank many colleagues at Computational Biology Research Center in Japan. CBRC researchers will give 2 highlight track presentations and 5 poster presentations. If you have an interest in CBRC, please visit exhibition booth number 29. Finally, I'd like to thank a lot of people around the world for praying for Japan. That's all I have to talk today. Thank you for your attention.